On the screen, actually, you know what I'm going to do? Let's do this. Let's move the TI so it's visible. Can you guys see inside the little viewfinder?
Yeah.
Is this screen pretty visible in that viewfinder right now?
Looks like it.
Oh, that sucks though. Hang on. That
Oh, no,
sucks.
you have to go down.
How about?
There, there.
That's good, Jess, in the viewfinder too? You can see, okay, sweet. I want to make sure, we're not going to use the computer very much today. It's mostly going to be back and forth board and TI work. Because what I want to do, I want to make, so let me recap. Go over to the sideboard for a second. So the question Jess just asked about the binomial distribution is fantastic because what you're about to see today, hopefully you saw it on Monday or whenever you got a chance to watch my little YouTube series of intro videos for what we're talking about today. There's a bridging I want to talk about today that I want to flesh out from the videos between discrete random variables and continuous ones. Is the temperature better, friends?
Yeah.
It's getting a little bit warmer? Okay. So tell me the difference between these two types of variables, or data as we used to call it basically data back in the day. What's the difference? Discrete random variables and continuous random variables. You have to think back now. You have to go back to the beginning of the course and think about these two terms.
One can be counted and one can be measured.
That's awesome, Athena. It's perfect. One's counted and one's measured. Which one's counted? Which one's measured?
Discrete is counted.
Excellent. So this, hopefully you can see that binomial distribution we just chit-chatted about is an example of this. As an example, we use the binomial. Think about some of the things we were talking about with the binomial random variable. Number of girl chickens in my flock. Number of times Max got his Crocs on the correct feet. Number of tickets, or number of people that don't or do show up for an airline flight. Those are all binomial things because you're counting those days. You can't have half a person not show up. You can average half a person not showing up, but you can't actually have half a person not showing up. They're whole number increments. They're countable things. There are many other types of random variables besides the binomial, but none of them are worth worrying about in an intro stat 1 class, honestly. There are other cool ones. We'll get to in 244, and if you take other stat classes past that, you get even more. But I actually had run in with one the past couple weeks. I think I was at you guys in the 243 class. I was talking about how I usually get a flat tire or two every year on my bike. I was telling you guys this. I got 2 in the past week. Was I bragging last week how I hadn't gotten one yet?
Yeah.
Yes, exactly. I got 2 in the last week. Yeah. So that's a perfect example of what's called a Poisson random variable. Number of flat tires per year. It's perfectly modeled by what's called a Poisson distribution, which is kind of like a binomial on a very small amount of steroids. But again, it doesn't fit your guys' needs as much as this does. This fits your needs for 244. It fits your needs for understanding what you read in the news. It fits your needs for when you have to model something in your life. Great for that. So binomial is great. And if you watch the video, I think it was the first of the 5 videos for Monday, I showed you a link between this guy and what I call the standard normal or the normal distribution over here. And this is what I want to spend a lot of time on today, is the normal distribution. This is when you don't care about the number of girls in your flock, but you're worried that your girls are getting too late because they appear to weigh not enough. You're like, oh God, Mary, she's lost a bunch of her feathers, which you can count if you want to. Or you just pick her up and you go, God, she's a lot lighter than she used to be. Well, you can't count weight. You have to measure weight. You have to put her on a scale to actually measure her. It wouldn't be the number of eggs you get per day like it was on your first out-of-class exam. It would be the average diameter or weight of an egg, or average thickness of a shell. See the difference? There's a nuance there, but it's different kinds of data. So these things are actually measured. And there are, like I said, just like there are many different kinds of discrete random variables, there are many different kinds of continuous ones. But the normal is really the only one I want to play with these last couple weeks we have together. Because I'd rather spend more time on one than not a whole lot of time in a bunch. I think it makes more sense that way. And once you understand the normal, if you ever have to tackle another one, which you will in 244 and maybe beyond, you'll have an understanding of the idea of the sliding scaleness of the continuous distributions like this one. Ish, fair? So, and the way I introduced this in that first video was I took a binomial and kept letting the number of samples increase from 3 to 5 to 10 to 50 to 100, and you notice what happened as the distributions got larger and larger as far as sample size go. You got this beautiful bell curve that just popped out of nowhere. Well, it didn't pop out of nowhere. It actually has to be there by definition. So that's kind of the tie-in between these two. This leads directly into that guy as your sample size goes off to infinity, which is pretty cool. Although we don't have to worry about sample sizes. You'll see what I'm talking about there in a minute. I spoke mostly of what's called the standard normal distribution in that video. But there's also the general normal, of which the standard is the subset. I'm thinking today, as far as like time allotment, I'm thinking like 80-20 standard general. There's a reason, a program I gave you guys. I gave you guys five programs I gave you in your TIs. One's disk fill, one's disk draw. Both of those you would use for the binomial. Two are called GOF and calc. You won't need those until 244 if you take 244. Otherwise, you just got 2 extra programs that you're not going to need on your machine. But there's one called STNormal. That's the one I want to play with today. And what it does for you is it does the annoying geometry that you would have to do otherwise. And I want to come back to that. I hinted at this in video 2 in that series of videos you watched on Monday, or whenever you watched it. I hinted at the geometry that you need to do, but I don't want you doing geometry. Every time I try to make you guys do a little bit of that extracurricular mathematics, you don't take to it very well. With good reason, and you definitely wouldn't take to this very well. You'll see why momentarily. But I want to kind of make sure we have the TIs handy, because I want to get into that STNormal program, make sure you understand how to run it. Cool so far? So this is just an overview, basically. This is the whole back half of this back third of the course is in this distribution right here. Excellent. It's week 8. Yeah,
It feels like
it looks like week 8. It does. I'll bring the energy up. I'll try to anyway. All right. Now, if you think back to discrete, actually, let's slide this back over here. If you think back to discrete distributions, what did the distributions look like? What did they look like? What was in here?
0 through.
Usually 0 through something, right? 0, 1, 2, you know. And what was in here?
Fraction.
Usually, yeah, it has to be a fraction, right, Tabitha? Something out of whatever this total was. So there's a probability associated with 0, whatever it is.
ratios all the way.
A ratio, a rate, a percentage, absolutely correct. And very importantly, what do these all sum to?
1.
Always and forever. Very nice, my friends. Very nice, always and forever. We can't do this for continuous random variables. Why?
Because they can't be measured? And so they
Well, they have to be measured.
I mean,
And you've actually struck it right on the head, Cassie. Why therefore, can't we do this?
because that has to equal to 1. So it has
Say
to
that
be
again, Kelsey.
There's no cap on what you can measure?
In what way? I love this. Suppose, for example, let's put an artificial cap on it. What Kelsey just said is very, very astute, actually. She said there's no cap on what you can measure. The trick with that one is, though, theoretically speaking, there are some discrete random variables that don't have caps on them. Not the binomial. The binomial definitely has a cap. But there was one I mentioned in class a few days ago called the geometric distribution, which is the number of times something has to try until it gets something right. There's no cap on that. I mean, if you have a robot arm that's trying to put a door on a car, it might never get the door on the car. It might just keep screwing up. And then there's no cap on that. It goes on forever. But let's put an artificial cap on. Let's say we are measuring the weight of one of my chicken's eggs, because I'm worried about that they're too small. Let's say the lightest it can be is 0 ounces, and the heaviest it can be is a pound, because I keep ostriches. No, because, so 0 to a pound, 0 to a pound. So we have a 0 and a 1.
How can it weigh 0?
Well, I'm giving it bounds. It can also weigh 1 pound. But I'm doing this. I'm trying to deal with Kelsey's very good point about capping it by capping it ridiculously. How much does a chicken egg weigh? A couple ounces, I'm guessing, right? 2 ounces. I never actually weighed one myself. I'm never worried about their weight because they always look fine and they seem healthy and happy. But here's the deal: if the caps are 0 and 1, Are those the only two values I can have in this column of the distribution? What else can be in there?
Could be
Everything
0.5.
0.5,
0.05,
0.25, 0.05,
Yeah.
point, Corey, please, Corey.
Infinite.
There are infinitely many values. How do you write infinitely many values? You don't. This is why mathematicians invented the number line, because they didn't want to have to discretely write 0. 0.000000000000000000000000000001. It's ridiculous to do that because you can't. Because even that number has something smaller than it. So what mathematicians did was they drew, let's come over here, they drew a number line, and for some reason it's been drawn horizontally. I don't really know why, but it's been drawn horizontally. And they placed, now, bear with me here. I'm going to put 0 in the middle of it. Now, there doesn't have to be 0. It could be anything. The question is, why would you put 0 in the middle? Well, there's no middle, because this goes on forever.
Right. Well, but the thing is that you have negative numbers and you have positive numbers.
Good. Do you remember what those are called, Raphael? I called these something in that video. Do you remember what they were called?
I know they're all real numbers.
They are. They are. They had a letter attached to them. Do you remember what letter it was? It was a Z-score. It's okay, and this is one of those things that you may have glossed over when you were watching it, didn't quite catch it. They're called Z-scores. I don't know why. Honestly, I don't know why they're called that, but they're called Z-scores. Those Z-scores correspond to the X's over there. Those correspond to the X's over here. That takes care of Corey's infinite issue, and the cap for that matter, because now there are no caps. It goes off forever in both directions, and everything's accounted for because I smoothly drew that line left to right. Perfect. Now, how do we deal with the probability column? How do we deal with that? Well, go ahead, Athena. This is where the bell curve comes in.
Well, I was going to say the y-axis.
Ex-
We're not
it
supposed
would-
to call it that.
You can. It's called the probability axis. You can call it the y-axis. But because it's the z-score, you know what, forget the z-axis even there. It's going to be a bell-shaped curve where the height of the curve above a certain value is the probability of that value. Now, don't get too hung up on what the scale of this is. FYI, this is about 0.4. So about 40% is right above 0, and then it falls off in a bell-shaped fashion towards the tails. Something else to think about, the tails never touch. They get infinitely close but never touch, which means if you go out far enough, there's still a probability, but it's essentially 0. Just like when we looked at the binomial one in the example we just did in the calculator, when you go out far enough, they eventually become 0. They're not really 0, they just round to 0. Same thing happens here. The interesting stuff that's going on in this curve is around the middle, which is 0. Now, speaking of this, you can tell by this distribution what the average is. This is the standard normal distribution, just so you know. This is the standard normal distribution. And based on this picture, what's the average? 0. The average is 0, based on that picture, and based on the fact that it has to be because it's set up that way. A slightly trickier question. What's the standard deviation, little sigma? This is one you'd have to probably remember from the video if you didn't get a
I remember
chance.
from the video, but I can't remember what.
It's okay. You remember it's 1 from the video, but you remember why? It is 1. The y, do you want the answer?
Yes.
Okay, perfect. Here is the function. That's the curve that makes that shape. I should make this z actually, because it's really z, not x, and this is really probability is z. That's the equation that makes that shape. If you want, Cassie, please don't worry. She looks great.
That looks awful.
Memorize it.
Sir, it's enough out of you.
No way.
That's the this equation makes that shape.
Yeah.
Okay.
But the program system normal I gave you draws it for you without problem. But this is the reason why that thing behaves the way it does. First of all, you see this E? Remember him from Math 111? That's 2.718281828. It's one of those goofy little constants from mathematics like pi. Because it's raised to a squared z, because it's raised to a variable power, that makes it exponential. And because it's exponential, that means it has an asymptote. Exponential curves usually have one-tailed asymptote. But because you squared the variable, it becomes an even function, which brings it back down again, which gives it two asymptotes. So that's the
Splits
reason.
it up.
Yes.
In the middle, and then it goes out.
Exactly. That's it should, as an exponential function, do this and keep going.
Right.
But that z squared brings it back down and makes it even and makes it symmetric. So that's why you get symmetry. That's why this you keep saying bell-shaped. The reason it's bell-shaped is because of that guy right there.
It's squared.
It's him. It's amazing. That causes the word bell-shaped for us. It's pretty amazing mathematically. As far as the 1, Athena, it's because of this guy right here. It's because of that guy. It's the constant they chose to multiply it by. On your out-of-class exam, I just had you guys, there was one where I had you sum up the P of X column, and it was I think it was greater than 1. And I think it was the last question. I said, go back. What constant would you have to multiply to get it to 1? And you had to figure out what that, that's exactly what this is.
I just divided it. What do you-
That's totally fine. But the thing is, that was a discrete random variable. Cassie, that's fine. That was a discrete random variable, and you could do that because you could sum. The problem with this, you're raising the perfect point, is how do you can forget about this too. I don't want to make anybody upset. But it answers Athena's question as to why it's up the way it is. A better question is this, and you know the answer to this already.
Oh.
You do. What percentage of the area? That's 100% of the curve. Yes, that's the correct answer. This is 100% of the curve. This is the 100% of the curve. If I were to draw a vertical line above -1 and a vertical line above 1 and shade all of that area between those two, what percent of, you can barely see that, can you? What percent of the curve?
One standard deviation.
Let's try blue.
65.
You can count boxes.
Well, okay, so I love both of those answers. First of all, I keep hearing 65s and 68s. The answer is about 68%. And you knew that from back in the day. Because back in the day, we learned that when you've got bell-shaped data, it's approximately 68% of the data is going to lie within one standard deviation. And that's what that range is, isn't it? Within one standard deviation of the average of 0. The question as to why is a slipperier one to answer. And here's the reason as to why. And you don't have to know this. This is why I gave you the software in the TI to do it for you. In order to get that area, that percentage, you'd have to start by figuring out what the probability of -1 is. Whatever it is. Whatever it is. Then you'd have to figure out the probability of whatever number is directly to the right of -1. What number is directly to the right of -1?
Are we talking
Are we talking
numbers or
zero or
tiny?
random?
I'm talking about continuous. Let me hear it over here. Negative point nine 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 nine
Yeah.
nine 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 nine
Yeah.
nine.
So I guess what you could do is get an overestimate and then an underestimate.
That's what
and then
calculus
figure out-
does, Raphael. So what you do, and if anybody's interested in more of a more rigorous treatment of this, I've got a little write-up on the enrichment page of the site that actually shows you what you do with rectangles to figure these areas out. But essentially, what you eventually do is you get the rectangles down so they're so skinny. What you're essentially doing is you're drawing one line at a time up, all the way from -1 to +1. Well, that's the same as shading it, isn't it? Now, what we just did right there was glossed over about 5 weeks of a Math 251 class. So if you want more, and it's all geometry. It's all geometry is what it is. You're creating, as Raphael said, rectangles, filling the shape with rectangles and adding up the areas of those rectangles. And the smaller the rectangles get in width, the better they fit the curve.
The more accurate it is.
The more accurate the result is. This is how all the geometry formulas that you guys know, 1/2 base times height, side times side, length times width, they all work on that principle. All of them work on that principle. It's just that we never learned that in grade school. You just kind of, here's a formula, go use it. And well, now you kind of get an idea as to why it works. And if you want more, like I said, it's on the page if you want to dive into it more. But you don't have to. That's why I gave you your program. Fire it up. Let's see how it works. Let's see how it works. Let's see how it works here. Oh, let's do this one, then we'll take our 5.
To normal?
It is to normal. So fire this bad boy up. Program to normal. To normal for standard normal. And I noticed I did say there are general and standard normal results. We're going to look at both of those today. We'll look at both of those today. Mostly standard normal. I want to stick with this curve for most of the day because I want to make sure you can understand what this program is doing and how it relates to that curve. Okay, so fire it up. Da-doom, da-doom. Okay, let's define something right now. A forward versus a backward problem. These are words I've made up because the formal words students don't like very much. The idea of the word inverse. I think it scares people from Math 111 land. You hear inverse, you start twitching. So I made up forwards and backwards problems. Here is the definition of a forwards problem. A forwards problem is one where you have z-scores and you need areas. So when I asked you what percentage of this is shaded, you have the z-scores, -1 to 1, and I'm asking you to find the area. That's my definition of a forward problem. A backwards problem, which we'll get to, is when you have the area, but you need the z-scores. You see how they're inverses of each other?
Basically, you're looking for the unfilled part or the outside of it.
Well, you can be, but you can also look for the filled part. The question is what you know and what you don't know. It's like an algebra class when you have x and need y. Sometimes you have y and need x. A forwards problem, if you will, you have x and need y. Backwards would be you have y and need x. Don't just realize this is forwards now. When I compare and contrast it with the backwards, it'll make a lot more sense.
What was backwards?
Don't worry about it right now.
Without your z-scores. you
Well,
gotta
yeah,
find your-
well, we'll come back to that. We'll come back. Just for right now, Jess, since you know these numbers on the horizontal, you know what they are, I've given them to you, you're looking for an area that's forwards. We'll come back to backwards, give you like 25, 30 minutes, we'll come back to it, I promise. So it's forwards. Is it between left or right? Well, I'm asking you to go between two numbers, so it's between. It's between. And then it asks you to give me the two numbers on the end, the bounds. -1, yep. 2, 1.
Right bound is?
Yep, right bound is 1. And then let it do its thing.
Oh, you just want the.
Yeehaw!
And it'll draw the curve for you. Let me get the light bulb around this.
That's cool. And even then, you could actually find out what n would be, and it will give you your whole total area.
That,
So
if you have, yes.
you could actually, by taking n, could then figure out what exactly your shaded area is in the middle, and then automatically find what's on the outside.
And that is how you can transfer back and forth between a discrete situation to a continuous one. You can take the percentage gotten continuously and apply it to a fixed total, and it becomes discrete. Exactly, Raphael. I like to keep them separated because for assessment purposes, it makes you guys happy if I don't mix and match them too much. But what this tells you is that roughly 68% of your data is going to be within one standard deviation, whatever that standard deviation is. So suppose, just to throw this out here, we're getting to this eventually in the course, the average height of a male is 5'9". An American male is 5'9", in a certain age group, with a standard deviation of, say, 2 inches. That means roughly 2/3 of guys in that age group are going to be between 5'7" and 5'11", which is within one standard deviation of the average of 5'9". That's actually valuable information. How tall should you make these doors? Right? How tall should you make a door in a building? Well, you'd hopefully make it tall enough so nobody would have to stoop, except for like professional NBA players, maybe. And code, I would hope, is set up for reasons just like that. We'll actually look at some of that stuff in this class, by setting up things like. Well, we'll get to that. We'll get to that. Fair enough. Let's take 5. You got that glazed look. Yes. We'll come back and do some more of these for sure.